this is some known fact that this is a always Artin gold standard ring. And what is the relation between the our varying rank and this apolarity? So this is the following result, which is the proof of which can be found in the book by Rabino and Kanu. So is the following, where geometry comes in the picture. So it says that if I have form f of degree d, and suppose it is expressed as the sum of r linear powers of linear forms, linear forms, then if and only if f_perp, the perp ideal of f, contains ideal of r distinct points. So this r is nothing but this r coming from in the summand. So the f can be expressed as the sum of r linear d powers of linear forms if and only if the perp ideal contains the ideal of x r distinct points, which I'm calling this as x, and these points are in the projective space over C. So this is where the geometry comes in the picture, and we of course want that these points are distinct. So if you can find the f_perp ideal, and if you can find some ideal of distinct points inside that, then at least we can we can say that rank of f is at most those number of points which you have found. And conversely, also if the varying rank is r, then you can say that f_perp should contain a r distinct point. So that's the idea. Usually, when if I want to find the varying rank of f, I will go to f_perp and I will see whether I can find where this is the ideal in the polynomial ring. And so our idea is to find some ideal of distinct points in this f_perp. And so this theoretically looks simpler, but finding sometimes f_perp is quite involved sometimes. In the two variables, something is very nice. We know many things, and this is classically well known by Sylvester also. So this is the following algorithm in the case of binary forms. So what is this? So there's an algorithm to find the varying rank of f in the case of binary forms. So this is the following. Suppose you have a polynomial ring in two variables, and I take a form of degree d. Then recall that in this case, the generic rank is given by the ceiling function d plus 1 by 2. Okay, and so recall if I have a binary form, then f_perp ideal, because S mod f_perp is a the T mod f_perp is a Gorenstein ring. Then we know that it's a common intersection because we are in the binary case, and hence it is generated by two forms G1, G2, where we can also say that degree of G1 plus degree of G2 is equal to d plus 2 by looking at the minimal resolution of T mod f_perp. So we know all the information about the f_perp. So in this case, what is the varying rank of f in the simplest binary form? So this is the algorithm Sylvester, due to Sylvester, where he says what is the varying rank of f in this case. So he says that we can assume that one of them have a degree less than the other. So let us assume that the degree of G1 is smaller than degree of G2. Then it says that the varying rank of f is degree of G1 if G1 is square free. Otherwise, it is degree of G2. For example, if you look at this form, this monomial, then the perp ideal is generated by xa plus 1 by b plus 1, and here because a is at least 1, this is not a free polynomial, so the rank is b plus 1. Right. So in the case of monomial, it's much easier because we can compute the perp ideal quickly. Right. And more generally, for any number of variables, the varying rank of monomials is known due to the result by Carlini, Catalivzano, and Jaramita. Where they compute the varying rank of monomials in a number of variables. So what is our work? Our work is on binary binomial forms. So what is the so before stating my result, let me just recall that. So even if you know the varying rank of monomials, it is not easy to compute the varying rank of binomials. For example, we have this lecture by Strassens, which says the following: if you have m forms in distinct set of variables, then the varying rank of the polynomial f1 plus f2 plus fm is equal to sum of the varying rank of each fi. So this is the conjecture which is still open, and recently Carlini, Catalivzano, and Jaramita proved this conjecture in the case of FIs are monomials. For example, it's easy to see that rank of this is equal to 2, and if you take two distinct monomials in CXY, it is easy to see that the rank of binomial is at most the rank of sum of rank of each monomial, because if write m1 as sum of linear powers of linear forms and m2 as sum of powers of linear form, then clearly we know the decomposition for m1 plus m2. But it's just that the gives the bond, but not the exact value of the rank of m1 plus m2. For example, if you take this binomial form, here the rank of which monomial by the observation which we had done just before, that the rank of each monomial is 4, but the rank of binomial is 3. So the actual rank of the binomial could be very less than the rank of the individual monomial. And for example, let me give one more example. So suppose you take this binomial, okay, then the per ideal looks like this one. It is easy to see that yr plus 2 kills this binomial, but it is not easy to check that this in fact is in the per ideal. And in fact, this G1 is of smaller degree than this one, and here one can easily check that this is in fact a square free polynomial in the F-per, and hence the rank of F in this case is R plus 1. Right? So even if you know the rank of each monomial in this case, but the rank of the actual monomial is different from the rank of each monomial. And similarly, one can see also in this example where the polynomial is xy4 plus x square y cube, and one can see that the f-perp is equal to x cube plus some polynomial d2, which I don't care. It's of degree greater than 3, and here the rank of f is 4 because this is not square free, again by Sylvester's algorithm. So what is our contribution? So we have proved and computed the varying rank of any binomial form in two variables, and which looks dirty, but we know the exact formula for the rank of any binomial forms. And importantly, if you take any binary binomial form, the varying rank of f does not depend upon these coefficients which are here, and it is not difficult to observe also. And more importantly, our contribution is the precise formula for the varying rank of any form in two variables. So how many times how much time I left?
Your time is up, so please wrap it up in a
Okay. So let me just so this is our result, and let me just say what is if you change the field. So the problem is more interesting when you change the field. For example, the more interesting field is the k equal to r. In this case, we cannot write the f as a sum of powers of linear forms, but up to scalar we can do that. So we can write f as a sum of linear combination of powers of linear forms, and the rank of f, the k-varying rank of f, is defined to be the minimum or possible when we write f as the sum of dth powers of dth linear combination of uh, forms. So now in the case of k equal to r, the problem is more interesting because here where the applications to real problems comes, and in this case, even though it's interesting, the problem is more difficult because as we see, there are, for example, even the generic rank for any form of degree d or r is not known. But fortunately, the polarity lemma is still true, that the f is a sum of linear combination of r linear forms if and only if the ideal of x, it contains the ideal of r distinct points. And here, as you see, the r distinct points, whether it exists or not, it depends upon the field which you take consideration. So that's why the rank is quite different in the case of if you change the field. For example, even for monomials, we don't know the rank of any monomial which has coefficients in reals. And let me remark that the rank of a real monomial can be very large as compared to the varying rank of corresponding monomial or complex. For example, if you look at this monomial, the varying rank we have seen for this monomial was either a plus 1 or b plus 1, depending on which is smaller and larger. But in the case of reals, it's always a plus b, which is the degree of the polynomial, which is quite larger than the actual in the case of complex. So that's where the rank can be quite different in the case of reals. And let me remark that there is no algorithm also in this case. And our referee was asking us to see what is the rank in the case of binomial, in the case of real binary binomials, but it is not easy as we see here, and because the perp ideal is quite involved in this case. Yeah, let me stop now. Thank you for your attention, and I wish Professor Dilip Patil a very happy and healthy life ahead. Thank you. And here are some references.
Thank you, Shrudevi. Questions, comments? Yes, I can see a raised hand. Please go ahead.
Yeah, I wonder in her talks, in your talks, you say about the point, and the R point. Is that true that you only work in the one-dimensional, in the only P1, and I don't know why you use the C is Y. Is that because of the characteristic 0, or is it a closed field? Like when you use the Sylvester algorithm?
So if I understand correctly, the question is that in this, why I use the field C.
Yeah, that's what. That's still hold true for the any arithmetically closed field.
So this apollarity lemma is true for arbitrarily algebraically closed field, and also I guess for any field, provided a characteristic of the characteristic of the field is large compared to the degree of the polynomial, this lemma is still true. But this algorithm is no longer true.
I see. So
this is true over C.
Yeah, and I have another questions. So you work on the set of point in only in P1. What happens if you go further like P2 or P3? So because here I look at I saw it here you have only 2 variables X and Y.
Yeah. So in our work we work only in the P1 because we know algorithm at least there. So in the P2 there are many works by Enrico and Oneto and so on. The problem becomes more difficult in that case because this algorithm is not there.
I see. So we cannot modify this algorithm, syntax algorithm for P2, right?
Yes, yes, yes.
Okay.
So there is no algorithm, and also because for example, if we take three variables, this perp ideal is, I just know it's a Goldstein ideal, but I don't know how many generators I will need for the ideal, and how that will help me to compute the weighting rank. So I don't know anything.
So this is about this is still open.
Yes, like we only use this lemma to compute the weighting rank. So only method which we have in many number of variables is this lemma, which is useful to compute in that case. Yeah, we don't know algorithm. That's still open.
Yeah. Thank you very much.
Yeah. Thanks for your question.
Okay, Nina.
My question is just this conjecture, somewhere in page 7 or 8, there's a conjecture. Yeah, this one, yeah, only. So what do we mean by distinct set of variables? Means each fi is a distinct set of variables?
Yes.
For example, f1 is not same as a variable of f2.
Yes, exactly.
But then these examples are certainly, because this is still a conjecture, so these examples, the variables are same.
Yeah.
So we don't know.
Yeah. No, I mean, I'm saying that this is the simplest case, and when you look at the sum of two, I should say, any forms, even in this case, this problem is still open. So one cannot guess the rank of sum of forms by just knowing the rank of individual forms, even if they are in the distinct variables.
So can we solve this for, okay, maybe quadratic forms may be easy because the quadratic forms links it with the determinant of that symmetric matrices.
Yes.
So
Yeah, quadratic form is simple.
Quadratic form is simple. There we don't have to worry.
Yeah, exactly. Because you can look at the matrix for this quadratic form, you will have
the same formula.
Yeah, same thing will work. It is true for that, but it is open in general. It's not known.
Not even small degrees, like degree 3 or 4, they have not been settled or they have not been investigated.
I'm not sure about the smaller degree. The only case I know which is true is in the case where each of them are monomials.
How old is this conjecture? Strawson's conjecture?
Actually, let me just remark, this conjecture was not in this state in the by Strawson, because there was a conjecture in the case of tensor. So the original conjecture by Strawson was in the case of tensor, which comes in applications when they want to study machine learning and so on. So the original conjecture was for any form which may not be symmetric. But then one tried to see whether it is true for the symmetric tensor forms when that is translates in this language in this form. So maybe that conjecture is solved um, in the case of not symmetric tensors, the usual tensors. So that is solved, but this is not yet known. This may be around maybe last 20 years, I guess. I'm not sure, but around 20 years.
Thank you.
Yeah.
Very nice talk.
Yeah, thanks.
More questions or comments? I have a couple of quick questions, Sridevi. One is that, did you say that the generic rank for monomials is also not known properly for real fields?
Generic rank of monomials. What do you mean generic rank of monomials?
I mean, see, if you just take the didn't it say the generic rank, or what did you say? I saw a result rank of x raised to a y raised to b is a plus b when a and b is non-zero, right? So in general?
In general, it is not known.
Okay.
It is not known.
Okay.
Yeah. So generic rank, I mean the generic rank of over C we know that is solved by Alexandra Helskovich. But generic rank over reals we don't know. if you take any form of. And for monomials, it's another problem. For monomials, we know the rank of any form over complex. This is again by Carlini, Derivation and Catalizano. But for any number of variables is not known. And for the reals, we know only this case, which is solved by Boyce, Carlini, and Geronimo.
And this is under standard gradation, right? So
Yeah,
when homogeneous. Now, for example, for your result on binomials, if you take the weighted gradation, is it going to be something very hard, or is it going to be almost the similar?
So weighted grading, I have not thought about.
And this is strictly for two variables, isn't it?
Yeah, our result was strictly for two variables. Yeah, because it's for two variables. But weighted polynomial rings, I think it is possible to find the at least the decomposition.
The decomposition. Okay. Thank you so much.
Yeah. Welcome.
Okay. Any other question or comments? Otherwise, we can move to the next speaker.
Hello, Indranath.
Yes.
Can you hear me?
Yes, we can.
Finally you are audible. Okay, good.
Thank you very much. Okay, thank you, Thiru.
You have some questions, sir, for Sridevi?
No.
Okay.
No.
Then thank you, Sridevi. And we just
welcome.
So maybe you can just stop sharing and
Okay.
No, it is done. Sridevi. Yeah, it is done.
Okay.
So the next speaker is going to be Parnasri. Parnasri, if you are around, please.
Yes, sir, I'm here.
If you have a screen to share, start sharing and let us check if everything is fine.
So can you see my screen?
Yes, it is. Yeah, maybe you can make it bigger. Yeah. Yes. Yeah,
So,
perfect.
shall I start now?
Maybe just in a minute.
Okay.
Okay, so I can, in the meantime, introduce next speaker for today's session is Parnasri Ghosh, and as you can see that she is a graduate student at the Stat Math unit of ISI Kolkata, and she will be talking on homogeneous locally nilpotent derivations of rank 2 and 3 on KXYZ. I mean the polynomial ring KXYZ. So you can get started, Parnasri.
Okay. So thank you, sir, for having me here today. And it's a really great pleasure to be a part of this event. And I have a very wonderful memory a few months ago that we joined a course on commutative algebra where one of our mentors was Professor Dilip Patil, and the memory was very nice. His lecture were very enjoyable, I would say. So let me start my talk today. It is about the homogeneous locally nilpotent derivation on of rank 2 and 3 on the polynomial ring in 3 variables. So this work is a joint work with my supervisor, Dr. Neena Gupta. So here is the content. So first, I will give some definitions, some useful definitions of regarding the locally nilpotent derivation. And then I will talk about the degrees of linear variables of KXYZ with respect to a homogeneous LND. And I will show a connection between the rank 3 derivation with this property. Then I will proceed to rank 2 derivations, homogeneous rank 2 derivations. And finally, I will discuss the Freeness conjecture of Jane Freudenberg. And we will see that how far we could proceed in this conjecture. So I am starting the definition of a low potent derivation. So suppose R be an integral domain which contains a field of characteristic 0. Now, a function d from R to R is said to be locally nilpotent if it satisfies this three properties. The first one is the additive property. The second one is the product rule, or the Leibniz rule for the derivations. And the third one is saying that for every small r in capital R, there exists a natural number such that dn of r is 0. So you see that this natural number is actually depending upon the element r. So that is why it is called a locally nilpotent derivation. And here I want to add something, that studying the locally nilpotent derivation is actually equivalent of studying the GA action on varieties. And these are very important tools for solving problems in affine algebraic geometry. Say for the cancellation problem, the Markov-Limonov invariant and Darkson invariant is a very important tool for solving those problems. So next I define what is called a degree function. So consider a totally ordered abelian group G. Now a function mu from G union minus infinity is said to be a degree function on R if it satisfies these three properties. The first one is mu of R is minus infinity if and only if R is 0. The second property is saying that mu of Rs is mu R plus mu S for every Rs in capital R. And the third property is about the addition, that mu of R plus S is less than equals to the maximum of mu R and mu S. Okay. So now every locally nilpotent derivation D defines a degree function on R. So we denote it by degree D from R to Z union minus infinity. And it is defined to be the maximum natural number n such that dn of R is non-zero. And when R is 0, we define it to be minus infinity. Now one can check very easily that degree D satisfies these three properties of a degree function. Hence it is a well-defined degree function on R. Next I define what is called an irreducible LND. So for an LND D over R is said to be irreducible if the ideal generated by the image is not contained in a proper principal ideal of R. Next, I define the triangularizable LND on the polynomial ring. Now, D is said to be triangularizable LND if there exists a system of variables x1 up to xn such that D of xi is contained in the polynomial ring generated by x1 up to xi minus 1 for every I from 1 to n. Now we go to the definition of degree of a locally nilpotent derivation. So let G be a totally ordered abelian group and mu be a pre-assigned degree function on R. Now, if we consider for a locally nilpotent derivation on R, if we consider this set, which is the collection of the difference of mu values of dr and r. Now, if the maximum of this set is in G or it is minus infinity, then we say that degree of D with respect to mu exists and it is defined to be the maximum of this set. Now here I want to tell you that it is not always true that degree of D exists for every degree function mu. For example, we have example both in characteristic P and characteristic 0 and those are affine such that the degree function does not exist. Okay. Now we define the homogeneous locally nilpotent derivation. Now we have a graded domain containing a field, say R. Now an LND D on R is said to be homogeneous with respect to the grading if and only if there exists a fixed element small d in G such that after the action of G on the nth degree piece that is contained inside the n plus dth degree piece for every n. Then we say D to be homogeneous and the degree of D to be small d. Now we define the rank of an LND over a polynomial ring over a domain. So consider a homogeneous art, not homogeneous, sorry. Consider any locally nilpotent art derivation on Rn. Then we define the rank of D to be, sorry. We define the rank of D to be minimum of R, minimum of R such that there exists a system of variables v1 up to vn of Rn such that under the action of D, only R many variables are surviving. So by this, I end the preliminary section. If you have any question, please ask. Okay. So now I proceed to the rank 3 locally nilpotent derivation. So our work basically started with the question of Freudenberg. So the question is, does there exist a homogeneous locally nilpotent derivation on Kn? This is the polynomial ring in n variables, which has degree 2 and rank n. So this question has negative answer for n equals both n equals to 1 and n equals to 2. So we investigated this question for n equals to 3. Now, before proceeding to the steps of answering this question, I'd like to state some important result in this context. So the first result is due to Miyanishi and Kambayashi. Miyanishi has proved this result for algebraically closed field, and then by a result of Kambayashi, it is proved for every field of characteristic 0. So if K be a field of characteristic 0 and D is a locally nilpotent derivation on K3, then kernel of D is a polynomial ring in 2 variables. So the next result is due to Zurkowski. This is the homogeneous version of the above result. So it is saying that if D is a homogeneous LND on Kxyz with respect to a positive Z grading, then the generators of the kernel F and G are homogeneous with respect to that grading omega. Now I state the result due to Degle. So this is saying that if D is a locally nilpotent derivation on Kn and kernel D is a polynomial ring generated by F1 up to Fn minus 1, then the structure of D is like this, that it is alpha times delta F1 up to Fn minus 1, where this delta is the Jacobian derivation and alpha is an element of the kernel. Okay. So next I define what is called a homogeneous LND of type LMN. So by the previous result of Degle, you can see that any derivation on K3, any locally nilpotent derivation on K3 is of the form alpha delta Fg, where the kernel is Kfg. Now we say that D is a homogeneous derivation of type LMN if degree of alpha is L, degree of F is M, and degree of G is N. So here these degrees are actually the polynomial degrees with respect to the standard grading. Okay. So now we state the steps where how we approached the question. So first of all, we notice that when D is a homogeneous locally nilpotent derivation with respect to the standard grading and having rank more than 1, then there exists a system of linear variables, say L1 up to L3, such that degree D of L1 is strictly less than degree D of L2 is strictly less than degree D of L3. Now one can say, okay, if we have any locally nilpotent derivation on K3, we can always get a system of variables such that this inequality holds. But here the important part is the variables we are getting, those are also linear. So this result plays a very important role in our proof. So now I want to tell you something that this result is true also for homogeneous R derivation on Rxyz, where R is a PID. But there are examples of one-dimensional normal domain where such kind of inequality does not hold. So at the end, if I get some time, I will show you the example. So let me proceed. Now we observe the this result that with respect to a standard grading 111 on kxyz, there is no homogeneous locally nilpotent derivation of type 0, 3, 3 and 0, 2, d plus 1, where d is 1, 2 or 3. So now we see the following steps. So let D be a homogeneous Lnd of degree d on kxyz, and d has this structure. Then the degree small d of capital D satisfies this equality. That is, d is actually degree of alpha plus degree of f plus degree of g minus 3. Now when d is 0, means the degree of the derivation is 0, you can observe from this equality that either degree of f is 1 or degree of g is 1. So what we get that the kernel contains a linear variable. That means the rank is reducing. Okay. Now for d equals to 1, if I need the rank of capital D to be 3, then from this inequality we can observe that D must be a homogeneous locally nilpotent derivation of type 0, 2, 2. For D equals to 2, if we want the rank to be 3, then again from this equality we can observe that it should be a homogeneous locally nilpotent derivation of type 0, 2, 3. And for D equals to 3, if we want the rank to be 3, then we have these three possibilities, that it should be a LND of type 0, 2, 4, or it should be of 0, 2, 3, or it should be a 2, 2, 2. Okay. Now if we see the previous result, so we have obtained that such LNDs of type 0, 3, 3 and 0, 2, d plus 1 for d equals to 1, 2, 3, they cannot exist. Now using the previous result and these steps, we conclude that there is no homogeneous locally nilpotent derivation which has rank 3 and degree less than equals to 3 on kxyz. So we obtained the answer of the question of Freudenberg for n equals to 3 is negative. It is not possible. All right. So next I am proceeding to the rank 2 homogeneous locally nilpotent derivation. So we have studied the rank 2 homogeneous locally nilpotent derivation, and we could characterize the triangularizable derivations among those. So let me show the characterization. Let D be an irreducible homogeneous locally nilpotent derivation of rank 2 and degree small d on KUVW with respect to the standard grading. Now, D is triangularizable if and only if there exists a system of linear variables xyz such that D is delta xp, where P has this structure, where degree d of x is strictly less than degree d of y is strictly less than degree d of z. And also we have calculated the degree d values of the variables, that degree d of y is 1 and degree d of z is d plus 2. Now if you observe this structure, then you see that this P is actually linear in the variable z, which is having the highest degree d value. So what is this saying, that if we give me any locally nilpotent derivation of rank 2 of this form, then looking at the structure of the of T, I can tell you whether it is a triangularizable derivation or not. Okay. Next, we get a connection between triangularizability and the degree of the derivation of rank 2. So it is saying that an irreducible homogeneous locally nilpotent derivation of rank 2 and degree p minus 2 is always triangularizable where p is a prime number. Now, looking at the proposition, we can see that the smallest possible degree of a homogeneous locally nilpotent derivation of rank 2 is 2. Okay. So we have characterized those derivations also. So we got that if D is the irreducible homogeneous locally nilpotent derivation of rank 2 and degree 2 on KUVW, where K is an algebraically closed field, then D is not triangularizable if and only if D is equals to capital delta XP, where P has this structure, where degree D of X is 0, which is strictly less than degree D of Y, which is strictly less than degree D of Z. And we have also obtained the degrees to be degree of Y is 2 and degree of Z is 4. All right. Now I proceed to the freeness conjecture of Jane Friedenberg. So before stating the conjecture, I would like to define what are called the degree modules. So with respect to an LND of R, if I take the collection of elements R such that degree D of R is less than equals to n, then this set Fn is called the nth degree A module, where A is kernel of the LND. Okay. Next, I define what is called a D basis. So let D be an LND of R and A is kernel of D. Then a basis for a free A submodule M of R is said to be a D basis if the elements of the basis have the distinct degree D value. All right. Now I state the freeness conjecture of Friedenberg, that let B is the polynomial ring in 3 variable, and D is a locally nilpotent derivation on B. If A is the kernel of D, then B is a free A module having a basis of this form. So if you see that this basis is basically a D basis. Okay. Now, using our structure of triangularizable derivation, we could prove that yes, the conjecture is true for triangularizable derivation, homogeneous triangularizable derivation on KUVW. All right. And also we have classified the the non-triangularizable derivations of smallest possible degree, and using that structure we could also we say that this such derivations are also having the freeness property. Okay. Next, I want to say the freeness property for general LNDs. So if we have an LND over Kn, where n is greater than equals to 4, then the freeness property does not hold in general. There are examples for where the flatness property, that Kn is not flat over the kernel of D. So there is no question of asking whether it is free or not. So flatness property does not hold even for higher dimension. Now, the freeness property of a locally nilpotent derivation D is equivalent to this fact that for every n, the nth degree module Fn is a free A module with a D basis. Okay. So what is known right now, that recently Degley has shown that every Fn is a free A module having rank n plus 1. But what is not shown yet, the existence of D bases. So if one can prove that okay, the Fn's are having a D basis, then the conjecture will be settled down. So I have told that if I, sir, do I have it in time?
You have about about 5 more minutes, definitely.
Okay, okay, sir. So I will show you the example for the normal domain. So let me go to that theorem. Yeah. So I have told you that this result is not true for one-dimensional normal domains. So let me show the example for a Dedekind domain. Okay. So this is our example. So consider the ring Rxyz, where R is this Dedekind domain, and we define a homogeneous locally nilpotent derivation of degree D as follows, where x1 is of this form. So now you can see that this x1 is a linear term, but this is not a variable of Rxyz. Okay. So what we obtain for this example is kernel of D is not equals to R2. Rank of D is 3. And the degrees of the variables are x and z are having degree 1, and degree of z is d plus 2. And there exists no system of linear variables v1, v2, v3, but such inequality holds. So if you see that, let me go to the example, that this x1 is in the kernel. This is a linear term, but this is not a variable. So when we have such equality for the degrees, then this inequality can hold if and only if we get a linear term in x and y, which is a variable, and it has degree 0. But in the kernel, since rank is 3, in the kernel there is no such variables, no such linear variable. So such kind of inequality cannot hold. So with this, I end my talk today, and here are the references. You can have a look. So thank you very much.
Thank you, Purnashree. Questions, comments? No, maybe you can ask her later also. So thank you, Purnashree. The next speaker
Okay,
is Kriti. Maybe we can start preparing and take a quick couple of minutes break, perhaps.
Yeah, sure.
I think we have a little time right now, right?
Yeah, yeah.
The second session starts at 11:20, if I remember. No, 11:15.
No,
11:15.
11:15. Yeah. Okay.
Amurtada, are you here? Yeah, I think.
Yes, Amurtada is here.
Ah, okay, good.
No, but yeah, Amurtada is
Yeah,
here.
he's here.
Yes, yes, I see you.
Shall I start sharing my screen?
Sure, yeah.
This is okay?
Yeah,
Yeah,
this looks fine.
fine.
Yeah, I'm ready whenever you say.
So Apurva, should we wait up to 11:15 or just start?
I think we should wait. We announced that was the time, so there might be some people who will join in at that time. Now we are on track, so I don't think there's any problem. Yeah.
So Kriti, when did you join IIT Gandhinagar?
So I joined in October last year.
Oh, so just few months.
Yes.
Before that, you were in Bombay IIT, right?
Yes.
Are you ready? Yeah, so maybe I just introduce the speaker now. So our first speaker in this session is Dr. Kriti Goyal from IIT Gandhinagar, a name which all of us are familiar, particularly with most of us are part of the ongoing commutative algebra seminar from IIT Bombay, and she is a key organizer of that. She was in IIT Bombay prior to joining IIT Gandhinagar. So she will speak on row factorization matrices and generic ideals. So start, Kriti.
Thank you, Professor Datta. It's my pleasure to talk today, first of all, on this occasion of superannuation of Professor Dilip Patil. I met him a few years back at an advanced instruction school. I was a student then. And of course, throughout the years after that meeting, I just not have been his student, but I've also been his tutor in several of the courses. And all of these experiences have been equally enriching. I have learned a lot from him. And I just wish him all the best of his health. And I just hope he continues to inspire a lot more students into this beautiful world of mathematics. So today I'll be talking about row factorization matrices and generic ideals. This is a joint work with Om Prakash Bhardwaj and Imanat Sengupta. So of course, I'll be talking about numerical semigroups, which was a well talked about topic yesterday, thanks to talks of Professor Harjag and Professor Sengupta. So today I'll take this liberty of just picking up a few definitions which I wish to recall. Just for today's lecture, I will not dig deep into the essence of numerical semigroups, but just touch upon a few definitions which I will need. So of course, starting with the numerical semigroups, of course, we'll be assuming that these semigroups are finitely generated. This means we are picking up S elements n1 up till ns over the natural numbers such that their common GCD is equal to 1. And by a numerical semigroup, we mean an additive submonoid generated by these S elements n1 up till ns. Of course, an equivalent way of characterizing numerical semigroups is looking at this complement set, which is called as a cap set. This is complement of the semigroup inside the set of natural numbers. And the way we characterize numerical semigroups is by the finiteness of this cap set. And since we have this cap set, which is finite, this means we can talk about the maximum element of this cap set. And this is what is called as the Freeness number, which is associated to this numerical semigroup. Of course, the other way of saying this as a Freeness number is that beyond the Freeness number, every natural number is an element of a numerical semigroup. The next term we define is the pseudo-Freeness number. Of course, these elements again are picked up from the cap set, but now they satisfy the property that these elements, which are I'm denoting by F, they should satisfy the property that F plus any non-zero element of the numerical semigroup should land inside the numerical semigroup. Of course, Freeness number satisfies this property just by the definition. And by the collection of pseudo-Freeness numbers, we have the set which we denote by PFH. So there's a connection between studying pseudo-Freeness numbers and properties of numerical semigroups. One such small connection is the definition of symmetric numerical semigroups. Of course, there are various ways to define it, but one of the important characterizations of symmetric numerical semigroups is via the cardinality of the set of pseudo-Freeness numbers. So we say that H is a symmetric numerical semigroup if and only if we have the Freeness number to be the only pseudo-Freeness number in the set. And of course, the other object that we associate with the numerical semigroups is the semigroup ring. This is the algebraic association of this so-called combinatorial object. So what is a semigroup ring which we can associate? So let's say we have a field K. Then the semigroup ring, which we denote by KH, is a subring of a polynomial ring. And it's generated by the monomials of the form t to the power h, where h varies over the elements of the semigroup. And of course, since we are associating an algebraic object with our semigroup, one would want to have this association so that we can study properties of semigroup in terms of the ring and vice versa. So one of this beautiful connection was made by Kunz in 1970, in which he proved that we have a symmetric numerical semigroup if and only if we have the Gorenstein property for the corresponding semigroup ring. And we have already seen that by symmetricity of the numerical semigroup, we have that the cardinality of the set of pseudo-Freeness numbers is exactly equal to 1. So indeed, pseudo-Freeness numbers in the background do play a role in characterizing certain properties of the numerical semigroups. So let's dig more deep into them. So the other equivalent way of defining pseudo-Freeness numbers is the following. Of course, we pick these elements from the cap set, but equivalently, one can define them in a way, in the following way, that we have this element F from the cap set which satisfies the property that F plus any of the generator of the numerical semigroup should be an element of the numerical semigroup. So instead of imposing this condition on every non-zero element, it's equivalent to have this condition on the entire set of generating set of the numerical semigroup. So we had n1 up till ns, so we had S generators. This means this equation, this condition rather, F plus ni being an element of H, gives us a set of S equations in S number of variables. And as soon as we have the setup of S equations, S number of variables, we can always go back to matrices. And this is what the idea that was picked up by Mascarillo in 2016. Given a pseudo-Freeness number, he associated an S crosses matrix with it using the above definition. So let's go through this. So we have a pseudo-Freeness number F, and to this we associate an S crosses matrix, which he called as a row factorization matrix, such that when we look at the ith row of this matrix, this is really a factorization of F plus Ni. And if one really looks at this matrix, this means we have the diagonal entries of this matrix to be -1, and all the other entries of this matrix are just natural numbers. Of course, we just have to make sure that the ith row is the factorization of f plus ni. And of course, as I say, it's a factorization of f plus ni as a linear combination of the other generators of the numerical semigroup. This factorization may not be unique. So given a pseudo-Frobenius number, we may be able to associate a number of row factorization matrices depending on how many factorizations of f plus ni for each I we are able to make. Of course, I'll also give an example of the same, but once we have the setup of row factorization matrices, what can we do with it? And of course, since Mascarello defined it, what was the thing that he could prove using this kind of tool or technique? And this is very interesting because something which is as simple as matrices could help him prove the following theorem. He proved that the Cohen-Macaulay type of an almost Cohenstein monomial curve in A4 is at most 3. And in other words, if I want to interpret this in the language of numerical semigroups, it just says that for an almost symmetric numerical semigroup, H, which is generated by 4 elements, the cardinality of the set of pseudo-Frobenius numbers is at most 3. And just to quickly recall what is an almost symmetric numerical semigroup, this just means that if you pick up any pseudo-Frobenius number, which is of course not the Frobenius number, then the Frobenius number minus this f is also pseudo-Frobenius number. So just a quick definition of almost symmetric numerical semigroups. But a theorem which seems to be as involved as this, Mascarello was able to prove it using row factorization matrices. And if one really looks at the proof, what is more interesting that he just counts the number of zeros which are inside these matrices for various pseudo-Frobenius numbers, and then he's able to come up with this kind of result. So row factorization matrices do have in them embedded a lot more information about about the numerical semigroups, and we'll see a few more connections, of course, later. But before that, let's just quickly look at an example. So I'll just pick up a simple example. We have a numerical semigroup generated by 3 elements, 5, 6, and 9. When we look at the gap set, it's just these elements 1, 2, 3, 4, then 7, 8, 10, 11, 12. Of course, they are there in the numerical semigroup. The next gap is 13. And beyond 13, every other natural number is an element of our numerical semigroup. And one can check just by the definition that 13 is a pseudo-Frobenius number. Of course, 8 is not, because 8 plus 5 is 13, which is in the gap set. And similarly for the other numbers, like 7 plus 6 is 13, which is there in the gap set. 4 plus 9 is 13, which is in the gap set, and so on. So 13 is indeed our pseudo-Frobenius number. This means we have to look at the 3 equations, 13 plus 5, 13 plus 6, 13 plus 9, write them as an n-linear combination of the other generators of a numerical semigroup. So while 13 plus 6 and 13 plus 9 have unique factorizations in terms of 5 and 6 and 9, when we look at 13 plus 5, it's 18. It can be written as 3 times 6. It can also be written as 2 times 9. And this gives us 2 possibilities of row factorization matrices which can be associated to our pseudo-Frobenius number 13. So just a quick example of seeing the connection of pseudo-Frobenius numbers with row factorization matrices. Next, I'll talk about this very particular class of numerical semigroups which are generated by almost arithmetic sequence. This was also hinted upon yesterday by the 2 talks, but I'll quickly recall it. So what do we mean by an almost arithmetic sequence? So of course, we'll begin with an arithmetic sequence. So let's say we have this strictly increasing arithmetic sequence, M0, M1 up till MP. To make it almost arithmetic sequence, we add an extra natural number, which just satisfies this property that now the GCD of this entire sequence, M0 up till MP, and the new natural number we added is equal to 1. And of course, we also have to make sure that this sequence forms a minimal generating set for our numerical semigroup H. So this numerical semigroup H is what is called as a numerical semigroup minimally generated by an almost arithmetic sequence. So these semigroups were actually studied very deeply by Professor Patil and Professor Balwant Singh in 1990. And this paper really led to a series of papers where they proved many things about this class of numerical semigroups. I'll just state the ones which I'll require. The first one being the paper by Professor Patil in 1993, where so there's this very technical setup which is given by Patil and Singh in 1990, which is associated to this class of numerical semigroups, but the setup may sound too technical when one sees it, but this setup turns out to be so much useful and powerful that the authors were able to find a lot more properties and a lot more information about the semigroups using that setup. Of course, the two main things were finding the minimal generating set of the defining ideal. This was a paper in 93. And the other information that they could gather was about the pseudo-Frobenius numbers. They could actually give a complete description of the pseudo-Frobenius numbers using that so-called technical setup. So this description was in 1999 by Patil and Sengupta. And if one wants to look at root factorization matrices now, which can be associated to this class of numerical semigroups, so the very first step is we need the information about the pseudo-Frobenius numbers. And this is what we could gain from this paper of 99. So using this information on pseudo-Frobenius numbers and the so-called technical but very important setup in the paper of 1990, we were able to actually give a complete description of the root factorization matrices. Of course, it's a little technical, and since we have this generating set for our numerical semigroup, which is generated by p plus 2 elements, this means the matrices are indeed huge, p plus 2 cross p plus 2. So in the interest of time, I guess I'll just rest with the fact that we were able to give a complete description of the matrices rather than giving you a complete picture of it. But what is more important here is what we can decipher now from this information. Once we have a complete description of the matrices, what information can we dig out more about these class of semigroups? And this is what brings us to the next topic of generic toric ideals. So I'll quickly recall what these are. So of course, in the beginning, I mentioned that if we have a numerical semigroup, we can associate a semigroup ring to it. The way we saw it was as a subring of a polynomial ring. The other way to see this ring is by looking at it as a quotient of a polynomial ring. And when we look at this quotiented ideal, this is what is called as the defining ideal of the semigroup ring, or the relation ideal, as it was said yesterday. So defining ideal or the relation ideal of the semigroup H. This ideal is a toric ideal and is generated by binomials. And this term of generic toric ideals, this was coined by Piva and Strumfels in 98. And the way they defined it is as follows. So if a toric ideal has a minimal generating set which consists of binomials with full support, that's how they defined it to be called as a generic toric ideal. We just need one minimal generating set which consists of binomials having full support. And why is it important to study such kind of or such class of toric ideals? They proved in the same paper that if we have a generic toric ideal, IH, then when we look at the corresponding semigroup ring, it is colored. And as a consequence, they were able to prove that this, as a consequence, says that the Poincare series of the residue field is rational. So this is a good enough reason to study more and more about generic toric ideals. So we have root factorization matrices associated to a semigroup. We have generic toric ideals, a special kind of condition for toric ideals in the semigroup rings. Is there a way to connect these two properties? And this connection was made by Iit in 2020, where he proved that the defining ideal is generic if and only if for every pseudo-Frobenius number, it has a unique row factorization matrix. And we also have the property that given any column of this matrix, all the row entries of that particular column are distinct. So these two properties were necessary and sufficient for characterizing the generic nature of the toric ideal. And this really beautifully connects the factorization matrices with the defining ideal. And so let's just quickly look at the example we saw in the beginning. We have a numerical semigroup generated by 5, 6, and 9. We saw that the Frobenius number, the pseudo-Frobenius number here is 13. And we saw two different row factorization matrices which could be associated to that pseudo-Frobenius number. And by the result of Iit, it kind of says that since we do not have a uniqueness in particular, it should say that we do not have the generic nature of the toric ideal. And this is indeed true when we look at this semigroup ring as a quotient of the polynomial ring. This is what we get. The defining ideal is generated by y cube minus z square and x cube minus yz. And indeed, when we look at the first binomial, y cube minus z square, it's not a full support. So just a quick example to put things into picture. So once now we have this connection, which was built up by Ito, and then we had a complete description of row factorization matrices for numerical semigroups which were generated by an almost arithmetic sequence. The next question was, can we build up this connection in this particular class as well? So if we have a numerical semigroup which is minimally generated by an almost arithmetic sequence, we have an information about the row factorization matrices. Using this result of Ito and the information, we could prove the following result. First of all, it says that if P is equal to 0, in particular, if we have a generating set of two elements, then IH is generic. It's kind of known. If we have P equal to 1, then under some technical setup, we have that the defining ideal is generic. Otherwise, it is never. So this is the class of rings where it's generated by 3 elements. The last thing we prove is that if we have P strictly bigger than 1, in particular, if the embedding dimension is strictly bigger than 3, then we prove that in the case of the special class of numerical semigroups, the defining ideal of the semigroup ring is never a generic tonic ideal. Of course, the other result which we prove is for the numerical semigroups which are complete intersection, in particular, the numerical semigroups whose semigroup ring is a complete intersection. And we prove the following. So if we have a semigroup, which is a complete intersection numerical semigroup, it has embedding dimension at least 3, then we prove that the defining ideal is never a generic tonic. So this is one information which in generality we could say about complete intersection numerical semigroups. So next, apart from this connection of row factorization matrices with the generic tonic ideal, there's also the other relation, which is the other connection between matrices and the defining ideal, which is given by certain binomials. These binomials are what are called as RF relations. So if you have a numerical semigroup and a pseudo-Frobenius number, we have a row factorization matrix. So let delta 1 up till delta S denote the row vectors of the row factorization matrix, which is an S cross S matrix. So we have these S row vectors, and by delta ij, we denote the difference of the jth row with the ith row.
Sorry, did it get frozen or?
I think she's back, yeah.
You are muted, Kriti.
Yes, yeah, I didn't realize when I lost the connection. Can you please help me where I lost it? Hello? Am I audible?
Start with the slides, RF relations. RF relations.
Okay. Okay, thank you.
Can you, RF relations.
Okay, sir, thank you. Okay, so there's, of course, another way of connecting row factorization matrices with the defining ideal. This is via certain binomials, which we call as RF relations. So that's how we define them. So let's say we have this numerical semigroup H, and we have a pseudo-Frobenius number F. And of course, to this pseudo-Frobenius number, we have associated a row factorization matrix, which is an S cross S matrix. So let delta 1 up till delta S denote the row vectors of this matrix. By delta ij, we denote the difference of two row vectors, delta j and delta I. So now once we have this row vector delta ij, which is a difference of two row vectors, we'll have certain positive components of this vector and certain negative components. So we separate them out. So delta plus ij denotes the vector which has all the positive entries of delta ij. And delta minus is the vector which corresponds to the absolute value of the negative entries of delta ij. And with this two vectors separated, delta plus and delta minus, we can form this particular binomial phi ij, which is x to the power delta plus minus x to the power delta minus. And just by the definition of it, one can easily check that these kind of binomials do land inside the defining ideal. And these binomials are what we call as RF relations because they come from the row factorization matrix of the pseudo-Frobenius number F. So given a binomial F in the defining ideal, we say it's an RF relation if it is RF-F relation for some pseudo-Frobenius number. And of course, this gives us an idea that these binomials they are indeed elements of the defining ideal. So the next question is, which was raised by Watanabe and Herzog, is that when can IH be minimally generated by these binomials, which we call as RF relations? These elements are indeed elements of the defining ideal, but when do they become a minimal generating set for this defining ideal? Of course, they also proved it in certain cases, precisely when embedding dimension is equal to 3, and the other cases when embedding dimension is 4, but the numerical semigroup has extra properties where it is either almost symmetric or it is pseudo-symmetric. So the reason we answer it is, and the way we answer it is the following. So the setup is, again, we come back to numerical semigroups generated by an almost arithmetic sequence, but now we restrict ourselves to the condition of the semigroup being symmetric. And we also impose this condition that embedding dimension is either 4 or 5. So under this setup, we were able to prove, using the information from the row factorization matrices, that the defining ideal has a minimal generating set which consists of RF relations. So in embedding dimension 4 or 5, under the condition of symmetricity, we were able to prove that for this class, the question indeed has an affirmative answer. So this was really the story about numerical semigroups. This means we are over the space of natural numbers. So this means the next question one can ask is, what happens over high dimensional spaces? Can this story be said over high spaces? And this is what I would like to touch upon in the last part of my talk. This is still an ongoing work, but I thought it's better to complete the story in high spaces as well. So what do we mean by, first of all, semigroups in ND? So of course, to begin with, our semigroups are finitely generated. So over here, we are looking for finitely generated submonoids of ND. Let's say they're generated by N1 up till NS. And this is what we'll call as the affine semigroups in high dimensional spaces. The next step is to look for the gap set. Over the set of natural numbers, our gap set was just the complement of the semigroup in the set of natural numbers. But over ND, there's not one natural choice that one can pick. So over here, what we do is we look for the complement of the semigroup inside its group. So let GS inside ZD denote the group generated by this affine semigroup. By gamma S, which we call as the gap set, this is complement of S in GS, and then we are just only restricting ourselves to ND. And then in this particular gap space or the negative space, we can now have a parallel definition for pseudo-Frobenius elements. These are again the elements from the gap set defining, satisfying the property that F plus Nj is an element of S for every J. So of course, when we are talking about high dimensional spaces, as I said about gap set, things don't follow parallelly, and there are more things which can fall apart when we talk about high dimensional spaces. The next hurdle being that, of course, we were able to define the set of pseudo-Frobenius elements, but what is it that kind of confirms that this set will be non-empty? We should first of all prove the existence of such kind of elements. And in order to prove the existence, we have to firstly define what are called as MPDs, or semigroups which have maximal projective dimension. So we say S has maximum projective dimension if, when we look at the corresponding semigroup ring, the projective dimension of the semigroup ring is S minus 1, or equivalently, we have depth to be equal to 1. And then it was proved by Garcia and of course a few more people in 2020 that the condition of the set of pseudo-Frobenius elements being non-empty is equivalent to saying that our semigroup is MPD semigroup. Of course, I would like to also mention here that the setup which this paper had was a little different from ours. The negative space they took was over the cone, but over here we thought for, of course, the later part of the talk, it was better to look at the complement set of S over its group and not the cone. So that's a slight difference between our setup and theirs, but when we look at the proof of this result, which is indeed a very nice one, the proof follows in our scenario as well. So of course, that's first observation. The second observation being that Of course, when we would want to work with pseudo-Frobenius elements, we want the set to be non-empty. This means we have to force the condition of the semigroup to be an MPD semigroup, and we do have a large class of rings which satisfy this property. But then we also lose one thing. Over the set of natural numbers, our semigroup rings were always Cohen-Macaulay because they were dimension 1 and they were domains. But if we are imposing the condition of S to being MPD semigroup in high dimensional spaces, this condition is equivalent to saying that the depth of the ring is 1. In particular, if your dimension D is bigger than or equal to 2, these rings will never be Cohen-Macaulay. So this one Cohen-Macaulay property is something that we will lose once we impose the condition on MPD. But we do have existence of pseudo-Frobenius elements, and then one can work more and try to dig in more and establish connections. Of course, the other observations are that the set is, first of all, finite, the cardinality of the pseudo-Frobenius elements. And by the cardinality, we really mean, we denote it by the type of S. Of course, it's not really the Cohen-Macaulay type, but just the type of S. And since all of the setup follows parallelly, one can also define row factorization matrices parallelly here. And of course, next thing I would want to touch upon quickly after pseudo-Frobenius elements is Frobenius elements, but before that, an example that row factorization matrices can really be defined in a parallel way. So we have this affine semigroup, which is generated by these 6 tuples. So this means we can form a semigroup ring R, which is quotient of this polynomial ring kx1 up till x6 over the defining ideal. This is our ks. Now, the proof of this result, which says S is MPD if and only if your pseudo-Frobenius, the set of pseudo-Frobenius elements is non-empty, actually gives a very nice construction of pseudo-Frobenius numbers using the resolution of the semigroup ring as a module over the polynomial ring. And this is the kind of construction that we'll be using here. So just a tiny observation here that when we look at the minimal free resolution of the semigroup ring, we look at the last is G. Of course, there may be many summands in here. You look at the shifts in the degrees at the very last step. Over here, we have 2 components, one having the shift as 16, 15, and the other one having the shift as 17, 18. These are the degrees of the last topmost SGs. To these tuples, the paper says that what you do is the following. You look at your generators, add them up, and then subtract this number from the degrees you obtain. So over here, first degree 16, 15, when we add up all our generators, we get the tuple 15, 12. We look at the difference. The first one says 1, 3. And then when we repeat the same process with 17, 18, we get the other tuple 2, 6. And one can check that these 2 elements are indeed pseudo-Frobenius numbers. And these are the only pseudo-Frobenius numbers which can be associated to our affine semigroup S. And now since when we have these 2 tuples, let's say we look at the row factorization matrix corresponding to 1, 3. So first row will correspond to factorization of 1, 3 plus 0, 1. That's 1, 4, which is one of the generators. And hence we get the first row and so on and so forth. So of course, the construction of row factorization matrix will follow in a parallel way as we had over the case of natural numbers. But of course, we can have a similar setup in high dimensional spaces. So let's look at the pseudo-Frobenius elements because even they have an interesting story over high dimensional spaces. First of all, over the set of natural numbers, we had a very unique pseudo-Frobenius element, and its existence was also guaranteed because of the complement set being finite. And all of this setup shatters when we look at high dimensional spaces. So the way we define pseudo-Frobenius elements, which is kind of a set to begin with, is by the following way. Of course, we pick elements from the gap set which we define, and now they should satisfy the property that with respect to some term order, F should be a maximum element over our gap set. And of course, parallelly, we can define symmetric semigroups over ND, and it's just the way to define symmetric semigroups is just by 2 conditions. First of all, the cardinality of this set of pseudo-Frobenius elements should be 1, and we should have existence of Frobenius element. This is an extra condition as compared to the set of natural numbers because we may not have existence of Frobenius element, which I'll just quickly say in one of the examples. So first example is S1, which is generated by these 5 tuples. This is symmetric because using the same step as before, we could look at the resolution of the semigroup ring, look at the top degree, subtracted with the difference of, subtracted with the sum of the generators, what we get is 7, 2. And 7, 2 is actually the maximum of this gap set, where this maximum, it's maximum with respect to this term order, which is the graded lexicographic order. So we do have an example of a symmetric semigroup because the cardinality of the set of pseudo-Frobenius elements is 1, and we have existence of Frobenius element. But we do have an example where the cardinality of the set of pseudo-Frobenius numbers is 1, but the existence of Frobenius element is not true. And this is what we have as an example. This is kind of really the Brzezinski curve, S2. I'll just quickly recall how it was defined. So we have a curve which is generated by 4 elements. And how it is defined for h bigger than equal to 2, we have these 4 elements, n1, n2, n3, and 4. We look at the projective closure corresponding to this monomial curve. This is generated by 0, n4, n1, n4 minus 1, n2, n4 minus n2, n3, n4 minus n3, n4, 0. So this is the affine semigroup that we look at in n2. And using the same step as above, we look at the resolution. This resolution was resolution of KS bar. This was given by Indranat Singh Gupta and few of his students very recently. We use this setup to pick out the degree shifts in the higher component, the highest component. And doing the same calculation as above, we get that this F, which is given by this tuple, is a pseudo-Frobenius element. But we were able to check that in the gap set, this particular tuple does not form a maximum with respect to any term order. So indeed, this is not a Frobenius element. So this kind of says that defining symmetric semigroups may not be even as trivial as we could do it over the set of natural numbers. Of course, lastly, I would like to wind up with coming back to the same thing again, the connection of RF matrices and generic toric ideals. We are still working on it, but the progress we have till date is that if we have an MPD semigroup, which we need to put as a condition because we want the set of pseudo-Frobenius elements to be non-empty, we're able to prove that if we know that the defining ideal is generic, then we were able to prove that for every pseudo-Frobenius element, the row factorization matrix is unique, and given any column, all its row entries are distinct. It's just one way result as of now. We do hope for the converse also to be true, but we are still working on it, so it's a little early for that. So of course, this is one of the observations that we make as a connection. The other result is about almost symmetric semigroups. The way we defined almost symmetric semigroups in the case of natural numbers, we can have a parallel definition in here as well. But of course, for everything which involves Frobenius numbers, we assume we have existence of Frobenius numbers. And once we have this, we were able to prove that if we have an affine semigroup generated by at least 4 elements, which is an almost symmetric MPD semigroup, then we are able to prove that the defining ideal is never a generic toric ideal. So these were just some set of observations that we were able to parallelly prove in the higher dimensional spaces. Of course, this is still a work in progress. And I guess with this, I'll end my talk. These are the set of references which I used in my talk. And thank you for your attention.
Okay, so so thank you. This lecture on a very interesting topic. Now, any questions, quick questions, comments? Okay, so if you don't have a question, the speaker later or maybe after the next lecture. So I think it is time for the next lecture to begin. So I invite Dr. Neena Gupta to, is Neena?
Yes,
Yes, sir. Ramanuj.
Yeah, so you, so how are you going to present it? You
are muted.
When you start your,
I have not prepared slides.
Okay, so you start, anyway, you share whatever you.
Can you see
Let
my
me
screen?
meanwhile introduce her. So Dr. Neena Gupta is with the Indian Statistical Institute.
Can you see my screen, sir?
I mean, not yet the main. Yes, now it has come. But there are some things.
You are
Hello?
going to write, right,
Yes,
Neena?
I'm going
There
to
are
write.
certain
Yeah.
things
So
on the
it is-
left hand
it is there.
side. Yeah, you can. We can
is there.
see it, and there is something on the left hand side. Can you eliminate that
Yeah.
to make it bigger? Or
Which one? Is
Yeah.
it not the big?
now your writing has gone away.
Is it
No,
not the
it is
biggest?
there. It is there. You were
No, it
writing
is there.
something.
Just
4
4.
or
Yeah, that's fine.
yeah.
It
No,
looks fine.
that's fine.
Maintain this size.
Okay, yeah, that's fine.
Yeah.
Is this okay? Miss handwriting is part is okay?
Yes. Yes. This is quite good.
Yeah. Shall I start? Shall I
So
start?
Dr. Neena Gupta will speak on stably isomorphic 4-dimensional affine domains. So start, Neena.
Yeah. So,
Yes.
so let me first say express my good wishes to Professor Dilip Patil. Yesterday we heard from many people that he has been a brilliant instructor. So I wish that he will.
Neena, can you speak a little louder?
Yeah, let me just try. Yesterday we heard from many people that Professor Dilip Patil has been a brilliant expositor. So I wish that he would keep continuing this activity even after the superannuation, and we will have an opportunity to meet with him regularly. Today, I chose a topic on cancellation problem, but it is slightly different and probably not so well studied. So let me give you a brief introduction. So throughout my talk, small k will denote a field, and for any ring A square bracket n will mean that A is a polynomial ring in n variables over R. So you have n algebraically independent elements x1, x2, xn, and A is a polynomial ring in n variables over R. So we say that two rings A and B, so all my rings are also affine domains. So these are affine domains. So are said to be cancellative if AN is isomorphic to BN. So I should better are said to be, so I should better say a ring B is said to be cancellative if AN is isomorphic to BN for some integer n greater than equal to 1 and an affine ring A implies A is isomorphic to B. So if this is a condition, then we say the ring B is cancellative. And this problem was known to have an affirmative answer, and this was due to Abhyankar, Ikin, and Heinzer. So this is Abhyankar, Ikin, and Heinzer. And this is a very famous result. The proof is also not difficult and was proved as early as 1972. And they proved that it's true. So if B is a one-dimensional affine domain, one-dimensional affine domain containing Q. And also true if you don't assume containing Q, then you may have to assume that's a normal ring or semi-normal. So let me not get into that. But more than affirmative answers, the counter examples are more famous. The first counter example was due to Hochster, and that was based on the existence of non-triviality of tangent bundle on the real sphere. So this was a example where you are working over a real sphere and you consider the tangent bundle over that. So that is basically the kernel of the, so let me call this ring R, and you have a ring homomorphism from R3 to R sending. So
Nina, do you mean x square plus y square minus 1 or plus 1?
Oh, sorry, I made a mistake here. So this is z square plus minus 1. So it's a real sphere. So this has three bases, R3. So so I can write it as RE1, RE2, RE3. Then I send E1 to X. So let me denote small x, y, z by the images of capital X, Y, Z in the ring R. E2 to Y and E3 to Z, and P be the kernel of this ring homomorphism, this module homomorphism. Then P is a projective module, and if you look at the symmetric algebra of this projective module P over R and call this ring B, then by the property of this projective module P, so this projective module P from the short exact sequence, you can see it's stably free, but using topology, one can show that B is not free. So using that, one can show that this ring B, after adjoining one more variable, is a polynomial ring in 3 variables over R. And this ring R is such that this isomorphism is an R algebra isomorphism, and B is not R algebra isomorphic to R2, but one can show that this will also imply that B is not isomorphic as over reals. So over reals, this is not isomorphic as affine varieties over real numbers. So we have an example. So here, what is the things we have? It's a 4-dimensional affine domain. In fact, it's a smooth domain.
In your second line, you mean non-isomorphic, right?
Yeah, this is not isomorphic, sorry. So it's a 4-dimensional affine smooth domain over real numbers. So this was a first counter example to the cancellation problem. And so there were some limitations of this example. So because we had an affirmative answer in 1 dimension, then we have a counter example in 4 dimension, and that too over a real number, not over complex. So this was a great achievement in 1989 due to Danielewski, and these examples are still very popular. So he constructed examples. So over the field of, so these are 2-dimensional smooth affine, and you can construct it over any field, means of characteristic 0, but you better you take complex number because that was more difficult to ask. And so what was shown is that so it was a family of examples, and so for each integer n greater than equal to 1, let b and b see x, y, z modulo x square, sorry, xy minus z square plus 1, then one can show that if you adjoin one variable to bn, then that is isomorphic to bm for all n and m greater than equal to 1. So if you're, and bn is not isomorphic to bm if n is not equal to n. So in some sense, we have a family of examples which are stably isomorphic.
Nina, I don't see an n in the definition of bn. What is?
Yeah, this is x to the power ny. Sorry. Sorry, I made a mistake. So x to the power ny. So these are stably isomorphic, but they are not isomorphic as rings. And we have a family of examples. So this was I would say, very good achievements. And after this, using this example, you can construct examples in higher dimension over any field K. And so in the general, this cancellation problem, A and isomorphic to B will imply A is not isomorphic to B, does not have an affirmative solution for n dimension of the ring is greater than equal to 2. But these examples, this example of Hochster and Danielsky, if we look at it carefully, so in this example, if I adjoin one variable, they become stably polynomial. So a natural question which one can ask is, suppose, okay, I should better write, does there exist a ring R such that Rn is, or I should say a fine K ring, isomorphic as in K algebra to An, but R1 is not isomorphic to A1. So does there exist some ring like that? And and we know that because of Abhyankar, Ikin and Heinze, that this will not be true if the dimension of the ring is 1. But dimension 2 onwards, the counter examples which we have, these Danielsky examples, they are all stably, if you adjoin one variable, it becomes isomorphic. So adjoining one variable, they become isomorphic. So the natural question is, does at all there exist some example? And the first example which we had in this direction is due to Zelonek. Let me just see. Yeah, and this was in 2009. He constructed examples over complex numbers, and the minimum dimensions were greater than equal to 10. And his example was again similar to the sort of Hochster's example, that based on the existence of projective modules which are too stably free but not stably free. And so in with Professor Asanuma, not one
it is
stably
not
free.
stably, right?
One stably free. So one stably free means after adjoining one free component, it does not become
Just
free.
add the word not.
Okay, sorry, but not one stably free. So with Professor Asanuma in 2018, this has appeared in 2018 in JCA. We had constructed an example. We have constructed an example. Okay, so Jelonek's example was smooth. So these were, in some sense, good examples. So we have constructed, so dimension of the ring is 4. It is semi-normal and affine. So this was in construction. Recently, Dubolos has constructed an example. So he had completed the story, constructed smooth affine rings over complex numbers, so which probably can be extended to any field of characteristic 0. So this was over real numbers over R and dimension greater than equal to 2. So for any dimension 2 onwards, we have rings which are A2 stable isomorphic but not one stably isomorphic. So in some sense, our example is a bit redundant, but it is good to see many examples of cancellation problems. So with this spirit, let me present you that example. So this is the example and this is the theorem. So in fact, what we have done is that we have given a recipe. So this theorem you can think of as a recipe for constructing counterexamples to two stably isomorphic, but not one stably isomorphic. So K is a field and R is a polynomial ring in two variables. So I will give examples where K equal to reals and complex numbers, and this you can apply to any field provided you get all these things. Okay, so R is a polynomial ring in two variables, and F is an element in R, and S is this quotient ring, and eta is this natural K algebra surjection, and with eta n, this induced ring homomorphism. So this MNR is the set of n cross n matrices over the ring R, and this is the natural surjection induced by this ring N. Suppose, so this with this information, suppose this F and eta satisfies this property, that the units, okay, so I should say what is S star. S star is the units of S. So the units of the ring S star is same as the units of the ring R star, units of the ring R, and which is same as the, because R is a polynomial ring, so its units are same as the units of the field K. So the units must be same, and in S, you should be able to find an invertible matrix P whose image in SK1. So I should better define what is SK1. So just let me go back to what this. So we all are familiar with SL and R for any ring R and an integer n greater than equal to 1. This is the set of n cross n matrices, n cross n invertible matrices. N cross n invertible matrices over the ring R. So you have a natural map from SL and R. As an inclusion, you can think that it is contained inside SL n plus 1R. What will you do? We will take a matrix M and we will send it to M 0, 0, and the last one you just add 1. So this is a natural way where we can think SL and R as contained in SL n plus 1R. So this is a highly non-commutative rings, and then we define SL of R, which is union of this SL and R. So this is the direct limit of this n cross n invertible matrices, and SK1 of R is nothing but the abelianization of this, that is you quotient it by the commutator. So this is an abelian group quotiented by the commutator of this, and so an element of this. So what we say when I say that there exists an element P in SK1 of R. So in my example, this is SK1 of S such that P is not 0. So that means P is not, so one can, so that means P is not, so P is a matrix in SL2 of S such that its image in SK1 of S is non-zero. Okay, let me just erase everything. What is happening here? So in the theorem, we need a matrix in SL2 of S such that its image in SK1 of S is non-zero. And this is a famous result due to, probably I don't remember, I think it's Suslin, who proved that SK1 of polynomial rings, if K is a field, is trivial. So this is nothing but K star. So that means every matrix can be written as a commutator of this after some variable. So in fact, any matrix, if you take a matrix in, okay, better. So this is a theorem. So in general, so what we have R equal to K2, and from K2 we surject it onto S, and here every matrix will become stably, so trivial by non-zero, I means better should say it's trivial. No, so K star is not the right thing. So K star is identity. Identity 0. So this is Suslin's result. Yeah, because or if you look 1 as the identity, then this is the 1. So, and this is S, and so we have a map from SK1 of R to SK1 of S. Even if this map is surjective, this map need not be surjective. So this need not be surjective. And our example depends on the fact that there should be a matrix P in SL2 of S whose image here is non-trivial. So then we can work with that. So let me just go back to that. So there exists a P in SL2S whose image in SK1 of S is non-zero. And further, if a phi is so R is polynomial ring in two variables and U, V, Z are indeterminate. So if phi is an automorphism of this ring, which is an, I should say it's a K-algebra homomorphism, and it fixes the element F. So fixes the element F means in some sense the element F, so F is that special element which we have selected. So this special element is fixed. The ideal generated by that is fixed. If this is the case, then phi should also fix the ring R. So this F should be so special. So if we can choose such an F in the polynomial ring Kxy, which satisfies these three properties, then we have these examples, and this is a construction of the example. So choose the matrix M in M2 of R such that its image is my P. So P is that chosen element. And then I construct this ring A. A is R. So R is a polynomial ring Kxy. And then U square V square plus F times RUV. So which is a subring of the ring D. So D is Kxy UV. And inside this subring, inside this ring, I am considering two subrings, A RU square V square and B R under this map. So alpha U plus beta V whole square and gamma U plus delta V whole square. So these are the two subrings. And if these two rings are such that this A and B are affine semi-normal domains, and A1 is then we can show that these are affine semi-normal domains. A is not one stably isomorphic to B, but A2 is if I adjoin two variables, then it is stably isomorphic. So this is the example, and I just give a very quick proof of number 3. The proof of 2 is a bit long, so I will tell it depending on the time. So this A2 is isomorphic to B2. So for that, we use the fact that this matrix P, if P is an invertible matrix, so P is where? P is in SL2 of S. So there exists a matrix P inverse in SL2 of S. So, and then construct this matrix P1. So this P1 is a matrix in SL4 of R. S, sorry. And then by Whitehead lemma, this is a very famous lemma which says that this matrix P1 is elementary. So elementary is something, let me not define. So if this matrix is P1 is elementary, then this map eta 4 has a lift. So you can find a matrix L. So this L is in SL4, which is an invertible matrix whose image is P1. So because it's elementary, we can have a lift here. So we can talk about an R algebra automorphisms of the polynomial ring RU, V, Z and W defined by sending U, V, Z and W to this linear transformation L. So L is that matrix. So this will be an automorphism. Okay. So now what we see is that this matrix, because L is a lift of this matrix, L is lift of P1, right? And what is P1? P1 is P0, 0 P inverse. So this matrix P, so for P we have a pre-image. What is that? That is my M. So similarly for P inverse, we have a pre-image M dash, but then that will be not same as this L. So it will be factored by some multiple of F. So considering that also, this matrix link automorphism L can be written as sum of these two factors, where G1, G2, G3 and G4 are polynomials in these 4 variables. So modulo F, it is P inverse. Okay. Now, if I apply lambda to this ring AZW, then I will say that the image is BZW, and that is very simple. You just keep applying it. So what is the value of A? A is this ring, and I apply lambda. So lambda will be applied to this ring plus this one. So I put Z and W inside this. Now applying lambda means I will apply lambda to this U, V, Z and W. So we do as it is. But what is lambda of U? So lambda of U is by this matrix formula. It is alpha U plus beta V and gamma U plus delta V plus F. And then by the same argument, because this alpha prime Z and beta prime W and gamma prime Z and delta prime W, these are linear, and this is an inverse. So this matrix has an inverse of P. We can get Z and W because we can, if at all there is a factor, we can adjoin it with F. So this will give us Z and W, and then this Z and W we can take out, and then we just get BZW. So this is very simple. And now I'll just give you a quick example over the real numbers. So over the real numbers, I can choose this F to be x square plus y square minus 1. And then it's an not so difficult exercise. And this is a theorem due to Miller. So Miller had proved that this matrix P is not trivial in SK1 of S. So using this, we see that the 3 properties and the other 2 properties one can check. So these other 2 properties, this one, this automorphisms fixing F will fix R, and this S star is K star. So we can take all these things for this small f, the circle, and then this is an example. So we can construct an example over the real numbers. We can also construct an example over complex number using this F. So F is y square minus x2 minus xy. So so this F is going modulo F. The ring S is this, which is a semi-normal ring. So I just calculated that it's a coordinate ring. So this is sitting inside CT. And so SK1 of S is K2 of C. So this is due to, just I don't remember exactly. So he proved that this field is uncountable. where, so there should be some matrix. So this matrix is not known to me, but at least there is some matrix P in SK1 of S, sorry, I should say SL2 of SL2 of S, whose image in SK1 of S is non-trivial, not zero, non-zero. So, and then we can construct these examples. So, how much time do I have? Do you have the time to prove this?
Time is actually, I think your time is over. So maybe. Let us see if anyone has any question or any question from the audience. So how much time do you need?
For the proof, I need actually 10 minutes. The one stably isomorphic, that is a long proof.
Then maybe drop it now.
Okay.
Can
Thank
I
you.
ask a question?
Yes.
Any? Oh, sure.
This K in this case, do we assume K to be of characteristic 0?
No. So in the proof, we are not assuming characteristic 0. So all it depends on the existence of these elements.
So the ring S is a R was KXY. So the ring S is a one-dimensional algebra. It's a
No, the ring is not one-dimensional.
S.
Ring becomes four-dimensional. So R is KXY, and the ring with
S is what? Just I was checking. S is R mod F.
S is R mod F. But
So
the example is over R.
But what I'm saying is over FP bar, for one-dimensional domains, affine domains, I think SK1 is trivial.
For one-dimensional affine domain, SK1 is trivial, yes.
So what happens in that case? Because you said there is a P in SL2S whose image is in SK1S.
No, for one-dimensional, I am not giving you the example.
Okay.
No, but who said SK1 of S is trivial in one-dimensional domain?
Over FP bar, I think Mrinal sir's result or something.
No.
If Ravi sir is here, I think he can confirm.
No, but what about this circle? This is a result due to Milner. I have not proved it. So
Okay.
this is a circle, right?
But
RXY mod
he
F.
is saying over FP bar.
Over FP bar.
Over the algebraic closure of the finite field.
Okay, for finite field it may be.
So then your field characteristic probably matters. That's probably what he's trying to.
So yeah, so as I said, the recipe works for any field. I am not using, but whether you can construct an element F or that will depend.
Thank you.
Sorry.
Quick request, Nina. Logistic. Yes. Could you save these slides and then maybe email it to me after the talk?
Yeah, I will show it. Thank you.
Yeah.
Just then stop sharing.
If there are no more, yeah, great. Thank you so much. And Dilip, are you still? Dilip, you are still here. Could I request you to come to the conference with a few words?
Can you hear me?
Yes, very much so.
Oh, very good. Once again, I want to thank all of you for.
So, any further question?
Oh, sorry. The talk was over. My bad.
Just one quick remark. Was there any?
Yeah, Nina is.
Was there any specific reason for arranging all the talks by the girls in the next session in the morning?
I think
Nina, just wait. I think Amartada is trying to say something, but Amartada, you are not audible clearly. Neither visible nor audible. Think some connectivity issues, perhaps.
Is he still logged in?
Oh no, now he is out, I think.
It wasn't so much a matter of age as it was sort of people who have known Dilip Patil for a long time. I had in fact also invited Grazia Tamone, Ping Lee, and at least a couple of others. Well, I wanted to invite one other person, but she has, I think, 7 years ago. And then Nina, in fact, I think I asked you as well, can you speak on Thursday? So I'd invited a few people, but somehow, as it worked out, everybody. Yeah,
I wanted to prepare slides, but I somehow fall ill, and so I was.
I hope you feel better soon, right?
No, it's just a cold, and because of that medicines, I was feeling a lot of sleepy.